Comparably, as Nicholas Copernicus introduced the heliocentric model, one more stunning revision of how we could decipher the universe could emerge, beginning a conversation known as the rise of cosmology. This development is marked by fundamental differences in our assessments and perception of the universe's critical properties, such as its age, size, and rate of expansion. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has halted this conversation with an image that defies material science. So, what exactly is this crisis, and how does the JWST contribute to it? Well, saying it contributes is somewhat misleading. It's more like a review that has been in progress. The crisis refers to how our understanding of the universe is being challenged, particularly regarding its age and size, which are linked by a broad margin of uncertainty. The introduction of the JWST has been crucial in advancing this discussion. Before its launch, we were limited in how far we could see into the early universe. However, with the JWST's enhanced capabilities, astronomers can now explore much more distant galaxies, offering new perspectives on the universe and challenging some of our previous assumptions. This progress allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming. This provides critical data that can either support or challenge our current models of the universe. To fully understand the crisis, examining the broader picture is essential. The standard model of cosmology, known as the hot inflationary Big Bang model or lambda cold dark matter, lambda CDM model, has been remarkably successful in explaining various aspects of the universe, from gravitational lensing to the large-scale cosmic web and galaxy formation. The lambda CDM model suggests that the universe began with a Big Bang, followed by a period of rapid inflation, and has been expanding ever since. It incorporates components like dark matter, which exerts gravitational influence, and dark energy, which drives the universe's accelerated expansion. However, every new observation, especially with cutting-edge instruments like the JWST, raises the possibility that our current model may be incomplete or require modification. The lambda CDM model makes specific predictions about the characteristics and behavior of galaxies at different stages in cosmic history. For example, it predicts that galaxies in the distant past should be smaller, less evolved, and contain fewer heavy elements compared to those in the nearby universe. This is because heavier elements form in the cores of stars and are distributed through processes like supernova explosions, which take time to occur. The description you provided discusses how the standard cosmological model predicts the evolution of galaxies and galaxy clusters, as well as the properties of the cosmic microwave background, CMB. According to this model, galaxies should be smaller, bluer, less evolved, and poorer in heavy elements at great cosmic distances. This would lead us to expect periods in the universe's history devoid of visible stars or galaxies. However, researchers have found unexpected evidence that challenges these assumptions, leading to a crisis in cosmology. The cosmological crisis centers on uncertainty regarding the universe's age. Different measurement strategies yield varying results, forcing cosmologists to reconcile these discrepancies. To address this issue, scientists use several methods to estimate the universe's age. One approach involves studying the cosmic background radiation, which involves unraveling the universe's expansion history using mathematical models such as the Friedmann equations, based on Einstein's theory of general relativity. These models help determine the expansion rate and, consequently, the universe's age at different points in time. The CMB, a remnant of the early universe, is a crucial tool for this calculation. Detailed CMB maps, like those provided by the European Space Agency's Planck mission, offer valuable insights into the universe's composition. However, these maps lack information on dark energy, a major component of the modern universe. Despite this limitation, researchers can use the Friedmann equations along with other observations to estimate the universe's expansion rate over time and, ultimately, determine its age. Another method for determining the universe's age involves observing exploding stars, specifically Type Ia supernovae. These supernovae serve as standard candles because they have a known intrinsic brightness. By comparing their known luminosity to their observed brightness, astronomers can determine their distance and, in turn, the universe's expansion rate over time. This method, used in the 1990s, played a crucial role in the discovery of dark energy, which is now essential in cosmological calculations. The Hubble constant, which measures the universe's expansion rate, is a key factor in determining its age. Although it is called a constant, measurements suggest it varies slightly. Since the Big Bang, About 13.8 billion years ago, the universe has been expanding consistently. NASA has noted that the implications of this expansion rate are significant. If the expansion is slowing, it suggests an unknown force, possibly dark matter, influencing the process. Conversely, if the expansion rate is accelerating, it could indicate the presence and impact of dark energy. In January 2018, researchers made an intriguing discovery. While some telescopes showed a variation in the universe's expansion rate depending on the observation point, the Hubble Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly slower rate in more distant regions. This discrepancy highlights the vastness of the universe and reminds us of Edwin Hubble's pioneering work in 1929, which first proposed the universe's expansion rate. Hubble's observations of distant galaxies revealed that they are moving away from us, demonstrating that the universe is expanding. This discovery became one of the foundations of modern cosmology. Now, if you were to observe the universe's expansion independently from your local region, you would see the same phenomenon occurring at the same rate as predicted by the Hubble expansion. Initial calculations were based on limited data, but technological advancements, such as the Hubble and Gaia telescopes, have allowed us to refine our measurements. Different telescopes use CMB readings to calculate the expansion constant. However, this method has its limitations, as the availability of supernovae for distant observations restricts our view of the universe. Since the discovery of dark energy in the 20th century, researchers have struggled to explain the inconsistencies between these different approaches to measuring the universe's age and expansion rate. As measurement technology becomes more precise, smaller variations arise, driven by the development of more advanced instruments. However, this progress raises more questions than it provides definitive answers. Although the discrepancies are minor, only 10 to 20 million years separate the different estimates, which is relatively small compared to the universe's 13.77 billion year age. They still warrant careful investigation. One possible explanation for this discrepancy is errors in our measurements of the CMB. Despite being one of the most reliable measurements, the CMB has undergone extensive testing since the Planck mission's launch in 2009-2. Our models. Resolving these uncertainties in supernova modeling could help reconcile the differences in measurements. This crisis in cosmology has been further exacerbated by discoveries made with the JWST. According to Neil deGrasse Tyson, the JWST has identified objects in the universe that challenge our current understanding. This suggests that our scientific framework may need a complete overhaul. However, the challenge is that we have no clear starting point for such a revision. To understand the scale of this scientific revolution, let's explore the origins of the universe. Around 50 million years after the Big Bang, stars, black holes, and star clusters began to emerge, possibly as early as 50 to 100 million years later. However, these events should be relatively rare. What remains unknown is how common galaxies were at later times, spanning events between 400 million years after the Big Bang and beyond. Recent JWST images reveal galaxies that are significantly more distant, and therefore older, than the standard cosmological model predicts. This suggests that our model needs a major revision. The discovery that the expanding universe relied on early galaxies is a crucial development. The JWST images show galaxies forming much earlier than expected based on current cosmological models, triggering a crisis in the field. According to the standard model, hydrogen should have been the dominant element in the early universe, and the formation of galaxies should have occurred much later than the JWST observations suggest. The redshift measurement indicates how much the light from distant galaxies has stretched as the universe expands, giving us clues about their age and distance. However, the JWST's discoveries contradict this by revealing galaxies that formed earlier than the current models predict. This challenge raises important questions about the limits of our current cosmological understanding. The discovery of early galaxies, much farther along in their development than anticipated, casts doubt on our assumptions about the timeline of the universe. These observations force us to reconsider how galaxies formed, evolved, and interacted in the very early stages of the universe, possibly requiring new models to account for the findings. As cosmologists analyze these new data, they face a pressing need to revise existing theories to incorporate the findings from the JWST. This could lead to a better understanding of the universe's origins, the role of dark matter and dark energy, and the overall structure of cosmic evolution. The crisis in cosmology, triggered by these revelations, marks a pivotal moment in the study of the universe, as it challenges long-standing assumptions and encourages a fresh perspective on the cosmos. Ultimately, the work of the JWST offers a unique opportunity to expand our understanding of the universe, even as it presents a crisis in our current models. The process of refining or even overhauling our cosmological theories will likely be a lengthy one, but it holds the potential for profound discoveries that could reshape our understanding of the universe's past, present, and future. One of the major implications of the JWST's discoveries is that our understanding of galaxy formation may be incomplete. If galaxies formed earlier and evolved faster than predicted, it suggests that either our models of cosmic evolution need revision or that some unknown physical processes influenced early galaxy growth. This could mean rethinking how matter clumped together after the Big Bang, how the first stars ignited, or even reconsidering the role of dark matter and dark energy in shaping the cosmos. The JWST's ability to observe these distant galaxies also challenges previous assumptions about reionization, the period when the first stars and galaxies ionized the surrounding hydrogen, making the universe transparent to light. If galaxies were already well formed in this early era, it suggests that reionization may have occurred differently than expected, possibly happening sooner or progressing in a more complex manner. The growing tension in cosmology. The discrepancy in measurements of the universe's expansion rate, often called the Hubble tension, has already caused significant debate among cosmologists. The JWST's findings add to this tension by suggesting that the structure of the early universe may not align with what we assumed based on CMB data and supernova measurements. If the standard model cannot fully explain these new observations, scientists may need to explore alternative theories. Some proposed solutions include new physics beyond the standard model. There may be yet undiscovered particles or forces influencing cosmic evolution. Revised models of dark matter and dark energy. These mysterious components of the universe may behave differently over time or interact in ways we don't yet understand. Changes in the rate of cosmic expansion. The universe's expansion may not be as smooth and uniform as currently assumed. Early black holes influencing galaxy growth. Massive black holes forming earlier than expected could have played a key role in galaxy evolution. The future of cosmology. The JWST's discoveries mark a turning point in modern cosmology. Over the coming years, more observations will help refine our understanding of the early universe. Scientists will need to analyze these findings, compare them with existing models, and potentially develop new theories to explain the inconsistencies. Other upcoming space missions, such as the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission, will provide additional insights into dark energy, dark matter, and the large-scale structure of a universe. Combining these observations with JWST data could help resolve the current crisis or lead to groundbreaking new theories about the cosmos. While the challenges posed by these discoveries are significant, they also represent an opportunity. As history has shown, whether with Copernicus' heliocentric model or Einstein's theory of relativity, scientific revolutions often arise from crises. The next great breakthrough in our understanding of the universe may be just around the corner.